So let's start the class. So my overall agenda is to review linear regression. Uh, okay, and before that, I want to actually review what is supervised machine learning to understand, because we are going to now bind everything in a single thread of understanding, and then we will move on to just explain briefly what has been discussed before about the linear regression and logistic regression. And essentially, my goal is to combine all of them into a single under the same roof. And then I will use the linear regression and logistic regressions framework to show that there are very special cases of this beautiful, broad class of neural networks. So I will show that there are special examples, and then I will use that as a pedestal to introduce to you neural networks and its fundamentals. And this will be happening over the next 3 weeks. So it's I want you to understand the mathematics, number one, the mathematics very carefully. I want you to actually code it out from scratch. So we will do it together. We will code it out from scratch. Of course, there is GPT and everything which can actually give you the code. But the whole idea is that if you code it out from scratch, then you can actually do research, do understand new things, right? And the final part is to do and apply it to a problem using a framework called PyTorch. These are all in libraries and all inbuilt, right? So usually people just do the mathematics and directly go to the libraries, but I want to help you read between the lines and help you actually build it from scratch, whatever in simple possible ways. Essentially, my goal is to help you understand what is going inside the PyTorch code, because this PyTorch code is pretty easy and everything can ChatGPT and AI can do, but you should learn the fundamentals so that you can think and develop new things. Okay, develop things that ChatGPT doesn't know. That's the goal of research. Okay, the goal of research is to create new knowledge that AI has not seen before. And that's where you progress the boundary of knowledge, right? So so you need to understand the fundamentals so that you understand what to innovate in. All of you got it, guys? Can you give a thumbs up? I hope all of you know. Superb. Vivan, all good?
So yeah, that was by accident.
Okay. Great. So let's understand, let's review in the first 30 minutes. Let's take our time slowly, comfortably to understand what are we trying to do here. So if you remember that there was one problem as far as recapitulate that, let's say you have this data. The data says that you have the first variable study hours. It's the first variable, and you have the second variable, the sleep hours. How many hours you sleep? And you want to use this to predict the score. Like if you sleep too much and study too less, it's bad. If you study too much and sleep too less, your mind will not work. So you have to find the optimum, right? So that's why it's very important to understand. And let's say you have been given data for this. Okay. You have been given data like 1, 8, and you score 50, 2, 7, you score 58. Okay. 3, 8, you score 64, 4, 6, you score 75, and 5, 7, let's say score 89. Okay, let's an example. So I will just make it small. But the whole idea is that what we're trying to do here, understand this very carefully, okay? That what is our goal? What is our general goal? Our general goal is you have an input data. Okay, you have an input. in this case x1 and x2, and you are trying to find and you're trying to predict an approximate output, predict, and you have the original output and you want it this to be close to each other. Okay, so let's write it in a more better form. So let's write it in this way. You have an input on a horizontal way. Input x, or let's make a box like this. Input, you are trying to know this relationship. Essentially, you're trying to understand the relationship between x and y. So this relationship is mathematically defined as a function. So it's going through a weird thing called a function, a machine. Okay, a function. And the output of this is this predicted y hat, and you have your already known like ground truth, let's say. It's called ground truth. This is the proper term. Ground truth. And what is the goal? The goal is understand what is given. Your given is the green. This thing is given. This thing is given. And this y hat is dependent on this. So this thing is not given. This is what you have to find out. Predicted naturally. These are unknown. So, but understand it's dependent on this, right? Predicted is dependent on y, how f. So essentially the whole unknown is f. Find the best f in terms of what? Best f such that the best f such that y hat, the predicted one, predicted value is close to the given ground truth. The given ground truth, right? So this is the basic idea. Okay, this is this basic simple idea. We want to find the f for all data, for all given data. Okay, given data. So this is the basic problem statement that we are trying to solve. Okay, all of you clear with this, guys? Can you give a thumbs up? Any questions? Anushka, any question? Okay.
No, sorry.
Okay, so yeah, please just give a thumbs up. Okay, don't forget to give that. If you have a question, please unmute yourself and ask me a question. So this is the basic idea. So what are we trying to do here? So understand, in mathematics, one thing is very clear, in any theory, is that simplicity is the goal. Okay, remember this, simplicity is the goal. So we will try to find, so what people try to do is that they try to assume the simplest possible function. Okay, a simplest possible function fx. So now when I say x, x can be, understand this, that is x can be a single number, a single number, or two numbers, or many numbers. For example, in this case, in this example, study hours and sleep hours are two numbers. In this case, study and sleep hours are two numbers, right? And the y is the score, right? And y is, example, is the score. So when I say x is represented as, you can generally mathematically represent as x1, that it can be multiple numbers, xn. Okay, this is mathematical representation. It can be any n numbers. So now why this and y can be a real number, just to say real number like this score, or instead of this real number you can have just categorical number, or you can say continuous and categorical. Call it continuous and categorical. Like there is a category, like for example, pass or fail. Pass or fail. Okay. So y can be this. Okay. So the input, this is called the input, this is called the output. Now understand, if it is continuous, it is called a regression. If it is, the problem is called a regression problem, understand this. If it is not continuous, if it's categorical, it's called classification. Okay. So the thing is that what is the simplest possible, so given this framework, okay, so let's first focus on regression. So understand the input x, which is nothing but, it can be n numbers, right? Is n numbers, n variables. Output y is a single variable. Okay, is a single variable. One continuous number. When I'm saying this, if you're getting confused, if it's too abstract, think of this example. Okay, think of this example in your mind. And these are all known. Okay, so the goal is, given the data set, you want to find a function f such that, so okay, so before this, what we will do is that we will denote the data set. The data set is nothing but, each data set is nothing but, each input has a one output. Each input has one output. So what we will do is, data set is nothing but a collection of x1, y1. So each input x1. Okay. So here is a deal. I will call x cap, above 1 as the first data set, because below 1 is inside that. So y1, x2, y2, xk, yk. So k data points. In this case, for example, this is x1, x above 1. Okay, understand this. 5 data sets. But this is x1 of 1. This is x1 of 1. Do you see the point? Oh, sorry, 2. Let's not go into too much of details, but yeah, these are k data points. Okay. So the goal is understand. So for simplicity, what we will do is that we will just say that we have xi. Our goal is to predict it goes through a function, it predicts yi hat. Okay. And we want it to be as close as possible. Okay, this is the basic setup. Okay. All of you got this, guys? Vivan, Anushka. Okay. Great. We want this to be as close as possible. So what's next? For simplicity, what people did is that they assumed the f to be linear because of the simplest, most function that is possible. Linear function. So how did they represent it? They represent it as w1. So the input is x. So understand this. The input is x. So essentially, it's nothing but a function. X is nothing but understand this n numbers, right? And the output is y. This is called y hat, and we are comparing with y. I'm drawing this thing over and over again because this will be helpful when you will understand neural networks. So the simplest possible function is what? A linear function which can be written as w1 x1 plus w2 x2, this is unknown, plus w3 x3 plus dot 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 w n xn plus an intercept term, intercept. Let's call it b. So when you have a simple, let's say 2-dimension, this is just simple, and you have these points. Let's say these are all x, y, y, like data points. Essentially, you're trying to find this best function, right? This best function. Now, this best function has some, is nothing but, you know that this best function is some yx plus b, right? So this y and b are unknown, and data will guide that. Similarly, when this is extended to this case, b is same, but these yi's are different for different variables. So this is the simplest possible function they can think of. Understand this carefully. The simplest possible function they are thinking of. So what they did was they got an x, they defined the y. Understand this f are defined by, this is also very important, this f are defined by these unknown variables y1, y2, dot 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 yn comma b. Okay, and output is y hat, which is f of x, and you see the how close are they. This is the setup. So when we say we have to find the best possible y, when we say that we have to find the best possible y, what we're essentially saying is that find the best possible weights, unknowns. So this w's are called weights, and this b is called a bias. I know it's different from slope and intercept, you know, but this is a different terminology, weights and bias. It's also not. Because if you fix the weights and bias, the function is fixed, right? So the whole idea is to find this the weights and biases from the data set. All of you got it? Perfect. So to redraw, we have x, we have this function, which are actually supported by this unknown weights and biases, and the output is y hat, which is nothing but f of x, and you want to find the closeness with y. So these are given. We have to find this, and naturally this, and essentially our goal is to find okay, this is the find. So the question is how next. Question is how to find it. So remember, our goal is to find this so that, remember, so that this y hat is close to y for all data points, right? Right, guys? In other words, y hat I is close, that is for the ith data point, y hat I is close to yi for all I, right? For the ith data point. So what, so the question is that there should be, when you say close, let's say if I'm saying that okay, I am close to this bottle, that means there's a distance between me and this bottle, so I want to minimize that. So this naturally is mathematically equivalent to saying that minimize some distance, which I am calling loss, between this y hat I and yi for all I. So where this is a loss or distance or whatever you say. Okay. Minimize this loss for all I. Now this is just for one I, so we will decide, we will see what are these loss functions. We will see. I'm generating an overall theory for you, okay, so that it stays in your mind. Loss and distance. So now before we move on, we have to define the final loss. Sorry, define the final loss, and this loss should be for all I. So what we do is we define a simple loss L, which is nothing but the average of all these losses. Okay, which is the average of all these losses, for all average of loss for all data points. Okay, average of loss for all data points. This is the basic idea. All of you got it? V1. Okay. So let's read out the diagram again, because the diagram will come over and over again. So we have an X, we have a F, and this F is defined by some underlying parameters, some W1, W2, Wn, and B, width and bias. Or let's call it parameters. So what we'll do, we will call it theta together. Parameters. Theta. Unknown parameters. So f of theta, and output is, so let's say I will call it a function, theta, we still doesn't enter it. Now it enters the function. Like we input the value of x, so it becomes x given theta. Like given means these are the parameters, okay? And this is nothing but the y hat, the predicted one. And we want to understand the difference between y and, so we have seen previously we are just saying that as close as possible, but now we will say it's a loss. Loss. Let's call it L. Now understand this, all this x, the x and y are known. So understand here this is unknown, right? And hence this is also unknown. F is also unknown, but yeah. But x is known. So hence the loss is also unknown. It's variable. And since for different thetas, for different parameters, the loss will be different. So let's take an example. Let's say x is 1.1 and 2.3, y is 72. Let's say, for example, very simple example. So this is x1, this is x2. So let's take w1 as 0.2, w2 as 0.5, and b as 1. So we get as the f. Oh, this is something we define. Assumptions. And we define f as f of x1 comma x2 as w1 x1 plus w2 x2 plus b. So therefore we get that the f of x1 comma x2 will have a single number, let's say 0, whatever, a very specific value, right? You can find it out, a value, it's known value, right? So what I'm saying is that as you change w, and then this specific value will be there, and then let's say your y value is something else, this, right? So whatever value you get, it will have a distance, it will have a number. So the loss will have a number, is a single number, is a number dependent on this w1, w2, w, like b. So what I'm saying is that this loss L is a function, is dependent on theta, the parameters theta. It is itself unknown because this only x and y are fixed. So to redraw, we have x, we have f, theta. This thetas are unknown. We have this y hat, which is f of x of theta. And then we have the loss function, which is itself a function of theta. Okay. So this is unknown. The f itself, the structure of f. So there are two unknowns. One is the theta parameters, one is the structure. In this case, it's linear, right? The theta is unknown, L is also unknown. Y hat is unknown. The only known are x and y. So understand that f structure is fixed in this case. And hence parameters. So that tells you that also tells you that, okay, what will be the parameters? Like we can change the function of x, if, and parameters, number of parameters and type of parameters will also change. Like I can make f as, in this case, f is this, right? is x1 y1 plus x2 y2 plus b. I can also make f as x1 square y1 plus x1 y1 y2 plus x2 square y3 plus x2 y4 plus b. I can make it different. So if I change the function, the parameters meaning will change. The parameters will change. Okay. But this is the core idea. So what I will do, instead of this just writing theta, I will just write like this, because I have mentioned theta inside. Like they're unknown, two unknowns. Unknown 1, unknown 2. Okay. And this will be fixed. We will also unknown. Like unknown means we will fix this. In fact, we will also fix this. The only variable will be theta. That's the whole idea. We will fix this. So this is the entire structure. Understand this this is so important. So be careful in understanding it. Okay. All of you understood it, guys? Any questions? Arav?
No, I understood it. I thought it for the thumbs up.
Yeah. So in linear, so therefore what we will do is that we will just write in this way. So for linear regression, to revisit, we will write all the, so we have the x as x1 x2 dot xn. We also have the y. This is the data set. So also we have the data set, sorry, this is the setup. We have the data set as x1 x y1 x2 y2 xn yn. Okay, sorry, xk yn, because n is already used in the number of variables. And understand, in regression it's y is equal to, yeah, y, which is a continuous real number. Okay, so now understand, the unknown is f. We will fix it. So fix f. So what we'll do is that we fix f and theta together. So we define theta, the parameters, the unknown parameters, as w1, w2, wn, comma the bias b, and the f of x comma x given theta as x comma, yeah, as a single number, x1 y1 plus x2 y2 plus xn yn plus b, which we define also as y hat, the predicted. Okay, and the loss L between any x, so essentially loss is between y hat, the predicted, and the original y, right? Since the regression means your, so we want it to be close. So what we define as a y hat minus y whole square. So we see how close they are, and we square it so that it's like, if it's -1 and 0 and 0 and 1, it should be same. The distance between 0 and 1 and 1 and -0 both should be same. So we want to see the distance. So this is the distance. So this is the setup of linear regression, guys. Did you understand? It's clear, right?
Yeah.
Pivan, Anushka.
So you can also use the absolute value as a loss function, right?
Which value?
The absolute value of y hat minus y as a loss function.
Absolutely. We can also use many other options. As I said, that we fix it. So understand. So there are three things, that is known, unknown. So there are three things. One is known, fixed and unknown. So we will call known as green, fixed as blue, and unknown as red. So here knowns are x and y. Just yeah. Data is also known. So all the entire data is known, all of them. Let's mark this. Theta is unknown, fully unknown. We don't know it. F is naturally unknown, but the F structure. So you can say the F structure is kind of fixed. It's fixed. Understand this carefully. The structure is fixed. And loss function is also kind of fixed. Loss structure. These are fixed. So,
And y hat isn't fixed, at least.
I mean, what I'm saying, yeah, I mean, you're right. Y has isn't fixed, but what I'm saying is that, um, yes, because y hat is dependent on both x and theta. Okay, so in
Yeah.
that sense, loss. So there are two things. One is the actual value, and one is the structure.
Yeah, the structure of it is fixed, but the values are not.
Yeah, of course, yeah, absolutely. So you can say like this, but what I'm trying to say is that structure of f and loss are fixed by us.
And how
Okay.
do we know that like the best possible approach for F is going to be linear or
Yeah. So that's where the neural networks come in. Okay.
okay.
So we try to first use simple things and then show. So one idea is that what is a good. So this is a good question. What is a good choice of f? There are many different reasons to, but I believe one important choice is like f should be able to
Simple? Be simple enough?
not really. I mean, there is simple like should be able to capture um
Bias or unbiased test data? Test data not known?
no, so it should be captured like it should be able to approximate any function, any good function.
Oh,
And also f should be simple enough algorithmically for computers to compute in a fast way. Interestingly, we will see that neural networks have this. Okay. But we have started with linear regression. So for linear regression, this is the setup. Okay. So what we will do interestingly is we will draw a diagram for the linear regression to make it easier, to look at better, to look better. So for let's say for x1, x2, we will draw like the input. This is just x. Okay, we will just extend this. So we will extend it as, so we are getting a single output y hat. What is that? So what we are doing is that we are multiplying w here, w1, we are multiplying w2 here, we are adding it up, and we are adding a bias term, unknown. This is the addition sign, and we are getting y hat, right? So once we are getting y hat, we are using this y hat and y to get, so you can say this y from here is also a constant, gives this loss function L. What it means is that it's x1 is multiplied by w1, x2 is multiplied by w2 and added, and this is the addition function, and the bias is added, and this gives output as y hat, and then we are using y and y hat to get this loss function. So this is kind of a circuit diagram of linear regression. All of you got it, guys? So to write it, these are unknown. Okay. These are known. And of course, these are unknown too. So, and yeah, summation is just summation. Doesn't make sense, but yes. So now, we will understand logistic regression. So logistic regression, same setup. X is x1, x2 dot xn, but y is now a categorical variable, like let's say 0 and 1, where 0 and 1 is not like 1 is greater than 0. 0 and 1 are two different categories. It is not like one is, there is no relationship between 0 and 1. Just like for brevity, we have put it like that. Then we have the dataset again, the same dataset as x1, y1 as the first dataset. Understand each xi has this actually. Understand this. Each xi has this n numbers in between. x2, y2 dot dot xn, sorry, xk, yk, k dataset, k data points. Now the difference is here that y is continuous and here it's categorical. So there should be some difference, and the difference will be showing up in the loss function and the function itself. So since it's 0 and 1, so what we want to do is that we want to predict. So output will be the probability of 0 and probability of 1. Like how much it is close towards 0, how much it's you will pass, how much it, what is the chance of passing, what is the chance of failing. Okay. So again, here the theta will be the same. Theta will be the same, exact. But since we are not directly predicting the y, but we are predicting the probability of getting y. So note, we are predicting probability of getting y instead of y, unlike linear regression. Okay. So if we have, okay, so for linear regression, what we did? For linear regression, we have x1, x2, dot, 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 xn. So we got this number of y1 x1 plus y2 x2 plus dot, dot, yn xn plus b, right? So what we do now is that we need to change it to a probability. We have to change it to a probability. Okay. So what they did was, so this is an interesting thing. So change to a probability, we have to make sure it's positive. All of them are positive and sum is 1. So how can you make, so what function is there which can make any number positive? Here x can be, this can be negative actually, understand this. So the function that makes any number positive is e to the power x. Any number positive. Let us non-negative, you can say. Any number yeah. In this case positive, but we want it to be a probability which is greater than equal to 0. So what we did is that we change it, we multiply each one. So here is a step. So we multiply each number. So we multiply this by e to the power this. So we want to say this is a probability of y. Probability of y of 1. Because if you get the probability of 1, you will automatically get the probability of 0, right? So we say that we multiply it with this. So let's call this as f of e to the power f of x theta. X, right? This is theta. So this is what we change to. But this is greater than equal to 0 now. But still, it is not, sum is, it's not less than 1. So what we do is that we have to make it less than 1. So what we do? We divide it by this. Something more than that. 1 plus that number. So that it's less than 1. Now it's less than 1. Right? Less than equal to 1. And greater than equal to 0 because it's positive. Why? Because we want to define it as a probability of getting 1 as a category. Okay? Probability of getting 1 as a category. This is important. Now, you may ask the question that, okay, I have 2 categories. What will happen if there are 5 categories? That's natural. All of you understood this, by the way? Vivan and Arav, can you give a thumbs up? Okay. So the next natural question is that, okay, this is good, but what will happen if I have 5 categories? What will happen? I have only 2 categories here, 0 and 1. What will happen if I have 5 categories? Okay. See, if I have 5 categories, what we will do is this. I have this x. Okay. I have this x. So let's first understand what we're doing for a single category. For a single category, we have this x. I will again redraw it over and over again as you have seen. We have f of theta. Then we have f of x of theta, which is y hat. And then we get loss function and y. Now here's another step because here we have not defined f of theta yet. So there's a step here. This before this step. That will happen is this f of theta is changed to this ESR of e to the power f of x of.
I'll have to go now because of the competition. Is that okay?
Sure, please watch the recording.
Yes, I will, Mr.
F of x of theta. And then what you do is that you multiply f of x of theta and change it to a probability. So this is now what? This is now predicted probability of 1. This is saying that, okay, the probability that x is category 1 is this predicted. And you already know that there is some y value, it's either 0 or 1. And again, we need a loss function here. So this is the actual y hat. the predicted probability. So what do we do? So rewrite the diagram again. I will redo the diagram again and again and again. X, this is a function unknown. We get f of x of theta. And then we get this y hat. This y hat is defined as this e to the power f of x theta by 1 plus e to the power f of x theta. And then again, we get the loss function from y. Same structure, there is only extra step, which is converting into probability from the previous one. So this extra step converts this into probability, converts f of x theta into probability. This is very important to understand. Okay, so what is this L? This loss is now, this loss can be defined as something like this. It's how the probability and so how they are different, and this is called binary cross entropy loss. It's minus of y log base e y hat one minus y log base 1 minus y hat. So why is this? This is called binary cross entropy loss. So now why this is chosen? So observe that this is nothing but minus of log of y hat if y is equal to 1 and minus of log of 1 minus y hat if y is equal to 0, right? All of you got it? See that if y is equal to 1, if the predictor is actual y is equal to 1, this is log of y hat minus of log of y hat. If it actually y is equal to 0, this loss function is minus of log of 1 minus y hat, right? So what is happening here? Any idea? So understand this diagram. If you draw the diagram of this, you will see that, let's say this is 0 and 1. Log of x is like this. This is log of x. Log of x is like this. So minus of log of x will be like this, inverted, right? Log of 1 minus y hat is like this. And can anyone say what of log of 1 minus y hat will be looking like? Any idea?
So log of what?
Log of, so let's say this is x-axis, this is y-axis. How will you plot y is equal to minus log of 1 minus x? So okay, so let me give you log of x minus 1 will be nothing but x is shifted towards from 0 to y. So this is log of x minus 1, right? If this is log of x minus 1, what will be log of minus of x minus 1? 1 minus x. So log of 1 minus x will be what? will be opposite of this, reflected along the y-axis. This is log of this, it will reflect along the y-axis. So this will be log of 1 minus x, and it is minus of log of 1 minus x. So minus of log of 1 minus x will be like this. So this is log of y hat. So let's call it y hat. And this is log of, sorry, this is minus of log of y hat. This is minus of log of 1 minus y hat. So what's saying that, observe this very carefully. This is saying that if, what this is saying, understand this very carefully. This is saying that you can see probably this meets at x is equal to 0.5. You can also equate it like log of y hat is equal to log of 1 minus y hat. And it will be essentially y hat is equal to 1 minus y hat, which means that y hat is equal to 0.5. So what it means is that if, understand this, so what it means is that if y is equal to 0, okay, if y is equal to 0, then understand this very carefully. If y is equal to 0, so essentially this will be something like a diagram will be like this. So as y increases, if y is equal to 0, if your predicted is more towards 1, sorry, I did it wrong. This is y hat. This is the f of y hat, which is, sorry, rather this. So if your y hat is, so if y is equal to 0, and if y hat keep on increasing towards 1, see the loss decreases, right? Sorry. Do you see the point? If y is 1 and y hat increases, loss decreases. I think I did a mistake. Yeah, Siddharth.
Wouldn't it start at 0, 0? Because at x is equal to 0, then y would be negative log 1 minus 0, which is negative log of 1, and that's always going to be 0.
Sorry, if y is equal to?
If x is equal to 0, then wouldn't like y be negative log of 1, which is always going to be 0? So it would start at 0, 0.
No. So think in terms of, um, tell me in terms of y hat and y. So we are trying to find this in terms of y hat. This loss is a function of y hat, right? We're trying to predict it. Like we are trying to see. Oh, okay, I see what you're saying. Yeah, I mean, okay. So what I'm saying is that if y is equal to 1, this is minus log y hat, right? What it's saying is that if y is equal to, okay, see, if y is equal to 0, this is this. That means it is this. So this is a piecewise function. Think of it too. So if y is equal to 0, this is this. If y is equal to 1, this is this. Two functions. This is a loss function. What it's saying is that if y is equal to 0 and if your y hat is moving away, sorry. If y is equal to 1, under this, okay, so understand, let me redraw it again. if y is equal to 1, the loss function is minus of log y hat, right? That's what we got. If y is equal to 0, the loss function is minus of log 1 minus y hat. So let's plot this. So what I'm plotting is this. This is y hat. This is this. Now there are two possible loss functions, right? Like the curves. One is this. We have seen this. So this is minus of log of y hat for y is equal to 1. Okay, so let's give it a different color. Okay, and this one, so let's say this is 1, this is 0. So what I'm saying is that this one is minus of log of 1 minus y hat if y is equal to 0. So let's see what it's saying. It's saying that if y is equal to 1, ideally you want to penalize the max if y hat predicted is equal to 0. That's what it's showing, that the loss, that means loss of y hat comma y should be max if y hat is equal to 0 and y is equal to 1, right? That's what it's showing. See, so it's decreasing. So for y, if y for y is equal to 1, this is decreasing. What it means is that as you approach towards 1, it becomes smaller and smaller. That should be ideally the case, right? As you approach towards 1, that means y hat, loss of y should be small and small, should decrease. And this also happens vice versa. For y is equal to 0, as it approaches towards 0, it becomes smaller. And in this case, as it approaches towards 1, it becomes smaller. The loss. Makes sense, guys? Vivan, Siddharth, Anushka, and Zaden.
Yes, sir.
Siddharth, is your doubt clear?
Yeah, I got it.
So for if y is equal to 1 and y is equal to 0, they are two different. So this loss function makes sense. See, in this case, the loss function was making sense because we are aware of this, what it's doing. But in this case, it was not sure. So it's my duty to tell you what it's doing. So now what it's doing is this. To recapitulate, we have x, f of theta, f of x of theta. Still, it's not y hat. Now y hat is defined as probability of this and then we have the final loss function, which is also dependent on y, right? So let's mark the unknowns. So unknown, kind of, we can say semi. Fixed, and the green part are this. Okay, and here also, like this is fixed also, this e is fixed, so this is also fixed. So it's this changes to probability. And I also define the loss function. So loss function is defined as this. Okay. Okay, so next, the next part is to represent this. We have actually discussed all of them. So we have discussed the loss function, we have discussed the functional type. Okay. So the next part, there are two things to discuss. One is the structure. So here, same structure. Here, let's say x1, x2. Let's do it in the circuit structure. We again have the same y1, y2. It's getting added here. Here is B added, the bias again. Here it's weights and unknown. And then here we get the f of x given theta. Okay. And then the y hat, which is, so understand here it's just getting added, but here there is a function. So there's a function here, the e to the power that by 1 plus e to the power that. Okay, it's called logistic. I will come to that again, what it is called. And then there's a loss function. Okay. So the next question, so to answer this, what this is generally called, just give me a minute. Yes. So the question is that I didn't answer it right away, but the question is that what happens if there are multiple for multiple categories? So what is done is that, let's say for same x, what is done is for the same x, three different f of x theta 1, f of x theta 2, and f of x theta 3 are formed. Okay, three predictions are formed. Okay, three predictions are formed. And then, so yeah, three predictions are formed. And then they are, so now they are transformed into now probabilities. So this will turn out to be, let's say for 0, 1, 2, there are three outputs. So three predictions are formed, and this should be turns out to be predicted probability of 0. Similarly, this will turn out to predicted probability of 1. This will turn out to be predicted probability of 2. First, the probability is important. So let's call it 1, 2, 3. Sorry, theta 1, theta 2. So three different functions are created to find out three different outputs. Okay. So now how the predicted probability is found, or what is done here? This is called softmax. It's very similar to logistic, but what we're doing here is that this f of x theta 1 is transferred to as e to the power f of x theta 1 So that it's positive, and then sum of all the e to the powers, f of x theta 1 plus f of x theta 2 plus f of x theta 3. Okay. So f of x is transformed into that. Similarly, f of x theta 2 is same, e to the power f of x theta 2, but below it's the same thing. And f of x theta 3 is transformed into again e to the power f of x theta below. It's the same thing again. If you observe, if you sum this up, you see that above it's the below sum only. So its sum is 1. So it's both greater than or equal to 0 and sum is 1. So this is called softmax layer. Okay. How to draw this? So let's say you have two inputs, x1, x2. So we have three, let's say, output. So we say as, so this 2 gives, let's say, y1, y2. For the class 1, let's call it y1s. This 2 gives y1, but for class 2, it's this y22. And this is class 3, y13 and y23. Okay. So this is, let's call it O1, O2, O3. Okay. 3 classes. So now these are transformed into softmax. So it's called SM, softmax. Same, it's like the same layer. You can call it a layer like this. All of them are actually run through a single function, because all are needed together, right? And the output is, this is called softmax. Output is y hat 1, y hat 2, y hat 3. Because we need 3 outputs, 3 probabilities, and the sum is 1. And now comes the trick. But understand, we have only one output, y. Right? So what is done here is that, let's say the probability is 25%, 25%, and then 50%. This is the probability output, predicted, let's say. But let's say actual is 3. The class is, let's say, 3. So instead of 3, what they will do is that, this is the y. Instead of 3, it will see that it will have 3 numbers. It's like 0, 0, and 1, like this. So what does it mean? It means actual is that 0 probability for class 1, 0 probability for class 2, and 1 probability for class 3. Okay. So this is the interesting. Now, this is the interesting. This is y1, y2, and y3. So how is it is defined now? Just like binary cross entropy, it was defined as y hat minus of y, sorry, y log y hat minus plus of 1 minus y log of, sorry, what am I writing? Sorry. So if you remember, this was nothing but minus of log y hat if y is equal to 1, and minus of log 1 minus y hat if y is equal to 0, right? So what we do in cross entropy, where it's for general, we do so what is this? If you observe, this is not, we can also write this as minus of log y hat of 1 and minus of log y hat of 0, right? This is nothing but probability of y hat of 0, right? So essentially cross entropy is nothing but simple. It should be minus of log y hat of if y is equal to 1, minus of log y hat of 2 if y is equal if y1 is equal to 1. Y1 means this, y2 is equal to 2, right? Minus of log. And if y1 is equal to 1, y like this is 1, then of course others will be 0. So this is defined as, observe, it will be, you can write the summation, and the summation will be over all the classes I from 1 to C, y hat, sorry, y I, sorry, yeah, yi log of y hat of I. Okay, this is defined as, understand this y hat is nothing but y hat of 1 pro y dot y hat of C classes, and y is nothing but y of 1 or y of C, and this is the final cross entropy loss. All of you understood this, guys? Yes or no? Please, the idea of it. Vivan? So we have got the entire, so this is important. This is called softmax. So device, understand this carefully. So we have x1. So if it's general, like let's say n of them, we get a single number, let's say output. So here w1, w2, wn, and here's a bias. And then you have the, so this is the y hat in this case. So there is a summation, sorry. And then you have the y hat. And then you have the loss function. This is for linear regression. For logistic, general, let's say n variables or input variables are there, okay? This is for, so understand this, all these calculations happening for each data pair. Say this is actually essentially happening for each data pair, like this. This calculation is happening for each data pair. Each data pair. So this loss is being calculated. And then it's averaged out. Okay. Yeah. And for logistic, let's see, the same thing again is happening. Y1 dot yn summation b, but there's an extra step. So we get y hat by sum after summation, same y, so not y hat, we get an output, which is same as f of x comma theta. Both are same as x comma theta, but here we have an extra layer of softmax. Okay, so let's call it SM, softmax, and then we get the output of y hat, and then L, and same. So understand, these are these are like, these things are like kind of operators. There's no parameters here, like These are operators. These are like functions. These are layers. Okay. So this is logistic regression. All of you understood this? Siddharth, Vivan, can you give a thumbs up? Okay. So what happens after this? So once this is done, both the framework is done. X, f of theta, fx of theta, then y hat, and then loss. This is the basic framework, right? Now we should not forget the goal. The goal is to find base theta such that L of theta loss is minimized. And that's where this is nothing but this is a function of theta. So this L is, let's say, like this. Okay. So we want to minimize the loss. This is theta, this is L theta. So we need to use calculus, borrow tools from calculus to find out this. And that's where we find gradient descent. I'm not revising gradient descent, but essentially what it does is the theta n is nothing but theta n minus 1. So let's call this, okay, I'm revising, let's say theta n minus 1 is this point. So it calculates the gradient at this point, the derivative. Let's call it derivative at f as at L. Gradient. The gradient is negative. So you want to go to the positive direction, opposite direction. So whatever is this theta n, we go to the opposite direction. That is del theta. Minus or del, but we want a step size. So essentially you are at a point of here and you want to go downhill. You have a step size and you have a direction, right? The step size is called eta, the learning rate. And this is the direction. And this is a point. So after this, it goes to here, theta n minus. So this direction is calculated at theta is equal to theta n minus 1. So this gives a sequence. So this is the derivative, which gives a direction. Sequence of points. First you start with theta 1, then you start theta naught, then you start with theta 1, then you start with theta 2 dot you theta n till it converges some theta star. So this is the theta star. This is not the theta star. This point here is a theta star, where the minimum happens. Okay. So this gives theta sequence of points which gradually converges to that theta star. Converges, like, rather becomes stabilized. Conversions are wrong, I guess. Stabilized. Okay. So this is all about gradient descent. So this gives you the final. This is the updated final best parameters. All of you got it, guys? Now this setup, this final setup, is same as neural networks. So neural networks has initial this x1, x2, xn, and then you go to the first layer. So here what you're doing in the first layer only, you are getting a single number in all of them, and then you are doing some layers over and over again to get the final y hat, right? So there is no layer inside. It's just single output right away, like this. Just some W1, W2, this. But number one question, how to introduce nonlinearity? Non-linearity. It's all linear, right? So we will see that there is, so essentially neural networks is defined as, so what we will do is that we will build inside some layers of linearity and non-linearity. Sequential. Linearity and non-linearity, step by step. Step by step, right? So we will see that X goes through some linear layer 1 and again a non-linear layer 1. This is together. Again a linear layer 2 and non-linear layer 2. Okay. And then there will be a final output. And then there will be the y hat. And then there will be the loss function. This is what we'll do next day. So this nonlinear linearity, so essentially, as if you remember, what we wanted to build a function such that f should be able to approximate in good functions and should be simple enough. So this neural network is simple enough by this sequential linearity and nonlinearity, pointwise nonlinearity and linearity. So we'll learn this tomorrow. And you can prove by universal approximation theorem that you can actually, it's a very good function. So we will address this tomorrow. Today's goal was to build this circuit idea in your mind using, so I did this, understand this. I did this, what is supervised machine learning, the regression and classification, linear regression, logistic regression, and linear regression to neural networks. Tomorrow I will be doing this in the next class. That how the nonlinearity and linearity plays together into the same to build this universal approximation, why it's a good function. Okay. All of you got it, guys? Any questions? I hope you got the entire idea together in place. So this circuit idea is very important. Super. The circuit idea will actually tell you that. So the circuit idea is the idea that how the message, the information passes through it, and these layers, these in between layers, this is the in between layers. This is the first layer, this is the second layer. In fact, with two layers, you can actually do anything. You can prove it. With two layers, you can approximate any function. That's why the neural networks are born. Okay. So this is the fundamental, this is the basic introduction to neural networks, guys. And the next day, we will be learning more about the fundamental structure of neural networks. Okay. I hope you liked it. I hope you enjoyed it. I hope you understood it better. So just here, so no need to understand too much of calculus for here, but the basic calculus here is that the derivative is important for the, because we need to know gradient descent. So tomorrow we will do the next day, we will be doing the, which is tomorrow, neural network fundamentals, and we will also try to code it if we have time. Okay, from scratch, all these things from scratch. Let's say a neural network from scratch. Okay, so we'll try to code, we'll understand code, but neural networks also have something more, like how to train. Those things we'll also understand. Okay, so all the best, guys. Understand there is one thing which is important, that code is the ultimate truth. So coding is extremely important. If you do not understand the code, you will not understand anything. So I taught you the mathematics, the idea. Next day, doing it from scratch, the coding is very, very, very important. Okay, I'll see you guys next class. Bye bye. Thank you so much. Any questions, guys? Vivan, Siddharth, Anushka, Jaden.
No, sir. Thank you.
Yes. Thank you. Bye.
I hope everything
Thank
is
you.
clear.
Thank you.
Okay.
Yes.
Super. Okay. Bye bye.